Yuri, it was a pleasure to be live in the last presential Ising lecture to speak about the spin glasses. So thank you very much for the invitation to chair this session in collaboration with Oksana Dobush. Okay, well, after this preliminary, I will introduce the first speaker. The first speaker is Jonathan Donges. I don't know, sorry, how is the right pronunciation of your surname?
Donges.
Donges, okay. Like, okay. Jonathan Donges for Potsdam Institute for Climate Impact Research in Potsdam, Germany. He is the future lab leader in this institute. He got his PhD at the Humboldt University. He has spent some time in USA. And in 2014, he was awarded by the Vladimir Koppen Prize. So the title of the talk will be Statistical Physics Analysis of Complex Social-Ecological System. Please, you can start when you wish.
Yes, thank you for the introduction. So I will talk about work that we did in my group over the past couple of years, and together with many collaborators like Job Heitzig, but I would also like to point out Jürgen Kurz, for example, and also Hans-Joachim Schellenhuber, the former director of PIC here, on applying methods from statistical physics, complex systems theory to the modeling and analysis of social ecological systems. And I would do a bit of a tour de force through different areas and point out relevant, research questions and areas where methods from statistical physics could potentially be applied with great benefit to answer these deeper research questions. So it's and what I will do is I will start with an introduction to this complex systems perspective on the Earth system that we are pursuing in the Future Lab that was mentioned in the introduction, the Future Lab on Earth system resilience in the Anthropocene. I will talk about the risk analysis of climate tipping cascades, and then move on to a more social ecological perspective on the modeling of social ecological tipping dynamics that is including then the human dimensions in the analysis. Now, just as to get you situated a little bit, this is the beautiful Albert Einstein Science Campus here on Telegraph Hill in Potsdam where we work. And I was wondering yesterday when I saw the lecture if Ising was ever here, because he lived in Berlin for some time, and it's not too far to Berlin from Telegraph Hill. Telegraph Hill is also interesting for climate science and for geology because it was created by the Ice Age. It's a terminal moraine of the last glacial maximum that was about 20,000 years ago. And here we can see, just to put the work that we're doing kind of to motivate it, to showing now global warming from Paleoclimate Perspective. We see that from the time when Telegraph Hill was created 20,000 years ago.
Excuse me, is it only for me that I don't see your transparencies anymore? If it is only my problem, do other people see the transparencies of the speaker?
I had the same problem, but now it's...
I see, but you need to click on in the lower part of the monitor of the screen.
Yes, I got it. Yeah, thank you. Sorry, yeah, thank you.
Okay, can you see it? Good. Yeah. So we see, just to show how much humankind has now started to change the planet. From the last glacial maximum to the Holocene, there was a warming of about 3 degrees. The human civilizations developed, and then we have the warming that has already occurred, about 1 degree of warming in 100 years, and future scenarios which go far beyond that. So global warming is not only about magnitude, but also about speed of warming. And this shows that the challenge of the Anthropocene that we are in today. So human societies have brought the planet already out of balance in this sense, and in the future this might become much worse. And these are the types of dynamics that we want to understand using our complex systems methods. I mean, this is very, very global. This was a very, let's say, macroscopic perspective, zooming in a little bit more. Something that interests us a lot are the so-called tipping elements in the climate system. And what this is, I'll get to in a minute, but these are critical parts of the climate system in different parts, ocean and atmosphere circulation, for example, biosphere elements like forests, but also monsoon systems, for example, that can undergo critical transitions under global warming. So they are nonlinear elements in the Earth system that could have potentially very large impacts on human societies if they are transgressing their critical thresholds. And not only that, these tipping elements are already dangerous in a sense by themselves, but they also interact. And there's a potential that tipping cascades or dominoes might be triggered by global warming. And this is also something we analyze using our network models. Furthermore, what I pointed out in this graph from the last glacial maximum to the Anthropocene, this the feature of the Anthropocene that human societies are now really an integral part of the Earth system, are really influencing climate processes, but also sediment transport, the water cycle, the biosphere on a global level. This calls for a whole Earth system perspective. So really looking at not only how humans influence the Earth system, but also how feedback interactions between human societies and these Earth system processes could play out. And this is something that we particularly focus on in our research with a focus on these nonlinear processes, on potential tipping interactions, domino cascades, and particularly also the role of social tipping elements in human societies that might be positive, so something that fosters, for example, a transition to more sustainable societies, but also something that could be negative, like the collapse of certain parts of social order. And overall, this complex interacting dynamics of human societies and the biophysical Earth system can give rise to a quite complex, of course, complex solution landscape, a complex co-evolution landscape. And this picture here of a potential landscape is only a cartoon of this, of course, but this is part of the task to really understand how the Earth system can evolve in the future under all these different processes, and what the risks are, what the opportunities are to still achieve a Earth system stewardship towards a stabilized Earth. And this is really the motivation of the work. So one is to understand these future trajectories of the Earth system in the Anthropocene. We are doing this more from a complex systems perspective, not so much from a more classical economic perspective or a purely physical perspective, as many other people are doing, for example, in the IPCC reports. So this is our perspective. And the second motivation, which has to do with this, of course, is that for the type of analysis that I very briefly outlined here, a new class of models is needed that can really integrate these societal and Earth system dynamics. We call them World Earth models. And this is because the currently existing models of global change, computer models, mathematical models that are developed, for example, in economics or in climate physics, they don't account for these human Earth system interactions, and they also don't account for many of the social cultural processes that are decisive in the Anthropocene. So things like dynamics of social networks, opinion formation, policy processes, changes in behavior, like in consumption, food choices, production, land use, social tipping points, or interactions between social and Earth system tipping points. And all these things, it's of course a very large field, but we are trying to work on some aspects of that. And now let me focus in a bit on the tipping dynamics in the climate system and what we can do there with our methods. Now, there are different types of climate tipping elements. They exist in the ice, in the cryosphere, in the ice system, so the big ice sheets on Greenland and Antarctica, in ecosystems like forests, permafrost, or even coral reefs, but also in the atmospheric and oceanic circulation systems. And but now in a bit more detail, these systems exhibit critical thresholds and which are in the climate field often called tipping points, and they often show the structure of cell and node bifurcations, and this is shown here for the Atlantic meridional overturning circulation, the AMOC, where a change in the freshwater forcing in the North Atlantic, which can be, for example, be caused by a melting of the Greenland ice sheet. This can lead to a collapse of the AMOC at the so-called Stommel bifurcation, where then the current state of a relatively strong AMOC, relatively strong overturning circulation in the Atlantic Ocean, goes to a collapse state where there's no or only very little overturning, which would have severe implications for climate in Europe, for example, because we rely a lot on the heat that is transported to Europe by the Gulf Stream, which is part of the Atlantic meridional overcirculation, but also the AMOC is responsible largely for creating the weather that we experience. So weather patterns could change strongly as well. Now, another example is ecosystems like the Amazon rainforest, where similarly these double saddle node bifurcation or cusp bifurcations can be found in, and what one can observe there, for example, is a transition between tropical forest and savanna states of these ecosystems, and for example, caused by changing rainfall amounts that a region receives. And this can not only be this is often viewed not only from a bifurcation diagram perspective, but also from a potential landscape perspective. So these so-called ball and cup diagrams, which are basically energy landscapes or potential landscapes, they are quite common as a visual metaphor in this field, but also as a technique of analysis. And this is just one way of looking at these critical thresholds of these different elements, is translating the critical thresholds of the individual elements to their equivalent in global mean temperature anomaly, so the amount of global warming. And what one can see here is that tipping elements are already at risk of transgressing into an alternative state starting at about 1 degree of global warming, which is a level of warming that we have already reached now today. So elements like the West Antarctic ice sheet, the Greenland ice sheet, sea ice, alpine glaciers, or coral reefs are already at risk to transgress critical thresholds. Other elements like the Amazon rainforest or the AMOC are at risk at larger temperatures. So this is just showing the current state of knowledge of where these thresholds could lie, but there's still relatively large uncertainty, as you can see in this. What we did is we focused on the potential for these tipping elements and cascades, because there is quite a challenge in actually modeling these Earth system tipping elements and their interactions. And with conventional microphysics-based climate models, because these state-of-the-art Earth system models that represent many of the underlying physics in very much detail and with very high spatial and temporal resolution. For example, the so-called AOGCM, so atmosphere, ocean, general circulation models, they often don't fully represent many of these tipping processes. For example, because they don't include dynamic ice sheets, many of the current models don't yet include dynamic ice sheet models, or because some of the physics representations or parametrizations are not good enough to show these nonlinearities, which are actually observed, for example, in paleoclimate records or known from an understanding of the underlying physics. So there's often still a discrepancy between our knowledge of that there should be these critical thresholds in these parts of the climate system and the ability of the really large integrated Earth system models to represent these nonlinearities properly. So this is important to keep in mind. And on top of that, there are considerable uncertainties, as I showed before, in the parameters of the tipping elements. So in the location of their critical thresholds, the timescales that are needed for transgressing from one state to the other, and also in the interactions, in the strengths and in the sign of the interaction between these tipping elements. So is it an amplifying interaction or is it a dampening interaction, for example? And finally, complex Earth system models are currently still way too slow for large-scale ensemble simulations, which are needed for taking all these uncertainties into account and for doing a proper risk analysis for the emergence of tipping cascades. And this is why we chose to use a network modeling approach with a statistical physics angle to it, complex systems analysis angle to it, where we model tipping elements as in a very, very simple way that is given by the equation here, a cubic polynomial which represents this cusp bifurcation, as it is shown also here in the figure. And we couple these elements using a linear interaction matrix, a network, a directed network, directed and weighted, and the tipping elements themselves, they can reside in an untipped regime or in a tipped regime, and there's a parameter range in the parameter C where there's a bistability possible. And what we do then is experiments. To put it very simply, we do numerical experiments here where we change the initial condition of one element to reside in the tip regime. So we tip one element, and then we see how this perturbation spreads in the network. And we analyze if a cascade like this here can happen or not under certain parameter configurations, for example, and under considering all kinds of uncertainties that we have in the real climate system. And we do this. We applied this approach here for a system of 4 coupled tipping elements, where we have relatively good knowledge that about their interactions and their individual parameters. And this is the Greenland ice sheet, the AMOC, so the Atlantic Ocean circulation, the Amazon rainforest, and the Western Arctic ice sheet. And what we do here is we propagate uncertainties between these in all these parameters and in the interaction network using a large-scale Monte Carlo ensemble, including about 10 million simulations. And we use the network approach that I outlined before to, for example, in the first step, to identify roles, emerging roles of tipping elements in cascades in this model. And what are these roles? So there is a possibility that a tipping element often appears as an initiator of a cascade. So that, and this is the case particularly here for the Greenland ice sheet. The Greenland ice sheet is an initiator of tipping cascades in 65% of all cascades that happen in this system, when you consider all the uncertainties, while the AMOC actually acts predominantly as a transmitter of cascades. So it participates in many relatively large number of cascades here, 28%, but doesn't initiate many of them. So this is already interesting because it shows, in a sense, where the weak parts of the climate system are here with respect to tipping cascades. Now, if we look into this in a bit more detail, also a bit more quantitatively, we can study, for example, how the effective critical temperatures, the effective critical thresholds change with increasing interaction strengths between the tipping elements. And what we find here is that the interactions between the tipping elements, they tend to destabilize the system overall. So the effective critical temperature decreases for all elements except Greenland. But for Greenland, we have a relatively large uncertainty in this increasing effective temperature. So it's very uncertain whether Greenland is actually stabilized by these interactions, as it has been actually hypothesized by other publications before. So we conclude that there's overall a destabilizing effect of these interactions on this network of tipping elements. And importantly, we find also that the risk, this is the lower panels, the risk for triggering tipping cascades increases quite significantly between 2 to 3 degrees of global warming above pre-industrial conditions. And the uncertainty in this risk is largest, particularly in the policy relevant warming range between 1 and 3 degrees. And this is actually the range where a lot of the political processes around climate change mitigation are taking part nowadays. So discussions between should the target be 1.5 degree of global warming, should it be 2 degrees, or are we still aiming for effectively larger warming levels? Now, moving on a bit to a bit more abstract level here. This is just a very brief teaser, but we've also studied the same type of system, but including noise now, and we find here that some quite interesting results. So it's one can actually describe the dynamics of this system of interacting stochastic tipping elements quite well, using tools from statistical physics, also in different types of complex network structures. So here including random networks, Erdős-Rényi, but also Barabashi-Albert and Watt-Strogatz networks. And it's possible to show that under certain conditions, this network of tipping elements actually behaves collectively like a single tipping element. So this is quite a nice connection between scales, because also in the climate system, in many cases, large-scale elements which are of interest, like a forest, for example, like the Amazon rainforest, actually consist of many small systems that interact. So many different patches of forest, for example, that can individually transgress between different types of vegetation, but they also interact, for example, via rainfall recycling networks in the atmosphere. And this is quite an interesting avenue, I think, to connect insights from statistical physics to these more applied studies of the climate system. Now, I would like to move on to the modeling of social-ecological tipping dynamics. I would like to, so we are now including the human in the picture a bit more explicitly, something that is done in some parts of science, of course, using agent-based models and network models, and this is also something that we will look at. So first, I would like to introduce very briefly the notion of social tipping points now in a bit more detail. This is a concept that has been very recently discussed a lot in the field of climate and sustainability, because it is a promising mechanism. It is seen as a promising mechanism to bring about rapid change that is much needed to avoid dangerous impacts of climate change, for example. And why is this the case? Because, for example, if you look at climate change, the rate of reduction of emissions that is needed to reach the Paris climate targets, so the targets of the Paris Climate Agreement, is very, very large. So if you compare these future rates of reduction that are needed, these are the colorful lines on the right. These become quickly much larger than rates of reduction of emissions that we have seen historically. Even the COVID-19 pandemic that has led to a reduction of emissions of about 8% between 2019 and 2020 this is relatively small compared to the reductions that are needed for 1.5 degree pathways, but also more historical emissions reductions, for example, during the Second World War and the collapse of communism, these are really small compared to the rates that are required in the future. And this is why looking at these mechanisms of phase transitions, so to say, in social systems is of interest to many people now, and we've also looked at that. These social tipping elements are systems are seen as systems where small interventions, small changes can have large effects. And of course, what is small and what is large is up to definition here. But there is a lot of studies. The concept on this in social science already. The concept has deep roots going back to the 50s, even earlier. There is also evidence for these effects in data, in behavioral experiments, but also in models, agent-based models, network models, for example, of public opinion, social norm changes, or investments on financial markets. And different clusters of such areas in society where social tipping could be expected have been identified. And this is something that here we pointed out in a more qualitative paper, that such tipping dynamics identified by experts could, for example, be found in financial markets, in energy production, in human settlements, education systems, information feedbacks, or the norms and value systems. So many different parts of society that act on very different timescales, from very rapid to much slower intergenerational changes, and across different parts of society, ranging from markets to customs, norms, and religion. And what we put forward in our modeling to study these elements is, again, a network perspective. We find this is quite useful even when starting from the social sciences tradition. Social systems are often seen or can be described as network-like structures that consist of agents or mesoscopic subsystems like organizations or social groups that are embedded within a broader social ecological structure. And we can now use this to define, or at least outline, what the definition of social tipping elements could be, when then saying that social systems can be called social tipping elements if, under certain critical conditions, a small change in this system or its environment can lead to a qualitative macroscopic change in the system, and that this often typically happens via network effects. And these network effects can be, for example, spreading dynamics, contagion, that does not only happen in epidemics, but could also happen, is argued to happen in behaviors or opinions, for example. But it doesn't only have to be spreading, it can also be a reorganization of the network structure, for example. So networks can polarize, social groups can emerge, or connectivity can increase or decrease, etc. So there's different dimensions of these changes. And so even if we put forward this working definition for our type of work, there is no commonly agreed definition so far of what social tipping elements are, and there's few quantitative studies of this so far. So most of this work is qualitative, even though, as I said earlier, there is a few quantitative results. But overall, we think that network modeling, because these systems have network structure, and there's it is a natural candidate to study these systems. And a method that we use a lot is so-called adaptive coevolutionary networks. What this is these are models where the local dynamics of the nodes of the network affect the topological evolution of the network structure, which then in turn affects again the local dynamics. So there is a co-evolution of structure and states in these networks. And this is of course a very general class of models, but this then we adapt and specify for different application cases. And I basically would like to look at a very small number of examples now of these types of studies that we did and how we apply statistical physics-like methods there. One is the network modeling of critical transitions in social movements. And why is this important? Because social movements are very, like the Fridays for Future movement on climate, are very important driver of social change and politics. And one has seen this in the past years. At least in Germany, the Fridays for Future movement was quite a big thing, and they had quite a large impact on here, for example, the percentage of German voters that think that environment is an important problem. There's a strong increase in this starting in 2018, which was caused by the dynamics around the Fridays for Future movement. And it's this type of dynamics that has been studied for quite a long time already in social sciences, in sociology, for example. And Granovetter created a very classic so-called threshold model, where for the emergence of collective action that is a useful tool for studying social tipping. And what we did in the study by our postdoc Mark Wiedermann is that we refined this model by introducing different types of actors, of agents in this model. So introducing instigators and potential supporters, where the instigators are agents that always follow a movement or always engage in collective action, while the potential supporters only engage if enough of their social surroundings, let's say enough of their friends, also engage in the movement. And then there's a third class, which are the people that never engage, so the passive ones that never engage in the social movement. And interestingly, it's quite easy to show that a micro foundation for this macroscopic Granovetter model is actually the Watts cascade model, which was published in PNAS in 2001. So it's a classic model for cascades on complex networks that when introducing these different classes of actors and doing a macroscopic approximation, is actually then becomes a macroscopic Granovetter type model. And this model can show social tipping points. This is here on the right-hand side, can show social tipping points in the social movement size, where varying the share of potential supporters or the share of instigators can tip the system from a state of low collective action to a state of high collective action. And there's the classic double fold bifurcation here, including a regime of bistability, and a visualization of this also shows here in the middle that it's a network spreading process. So this is quite an interesting class of model to study further in terms of really characterizing the phase transitions that emerge, introducing stochasticity, etc. So there's a very rich dynamics to be expected. We only scratched the surface here, I think. What we did with this model was a more so far a more applied study, where we combined this model with very rich data on sea level rise projections, population elevation distributions, and data on cross-national climate change concern. Because we said countries that where people are generally more concerned about climate change are countries where there's a larger share of potentially acting population, and this is shown. This is shown in panel A. What we see is that, for example, in countries like India or Brazil or South America in general, or Africa, people actually have relatively higher concern about climate change compared to, say, Europe or North America. And one reason for this is probably that people have a lower distance, psychological distance to risks than people in more industrialized countries, because they are much more exposed to risks of climate change, like extreme events or sea level rise. They have less protection, less resilience. And what we find when applying our Granovetter type model to calibrate it to these data sets is that generally increasing concern increases the potential for tipping to collective climate action to emerge. So concern makes the systems more critical. Anticipation of future climate impacts, of future sea level rise, in turn, tends to move the system closer to the actual tipping point, to the actual phase transition. And what we find lastly is that it's for these social tipping elements, it's more relevant to study the potential for interventions to kick the system into an alternative state, rather than looking for where exactly a critical threshold of phase transition is. And the reason is that the tipping dynamics arises from various different factors, typically not from a single control parameter, and the so-called noise-induced tipping is also more prominent than so-called parameter-induced tipping. So often it's more the stochastic events, agental interventions, or extreme events that kick a system that is already critical to another alternative state than a classical transgression of a critical threshold. This concludes the global perspective. I would, to close with my examples, I would like to move to one final class of models, which describes systems on a somewhat smaller scale, and also looks at truly interconnected social ecological dynamics. And one example for illustration of these types of systems are so-called Balinese water temple networks. This is really just to show that these types of systems, what to imagine of these types of systems. And what are these water temple networks? These are networks of villages in Bali where people meet yearly to negotiate how they use their resources, their local resources. And they can decide to move to use more of their resources for water, namely, or less. And they have different reasons for making these decisions. And we put this into an idealized model of our own, which has more a motivation of a classical resource use model. So it's a co-evolution of opinion formation or decision making on social networks and renewable resource harvesting. And we have these different actors, which you could imagine as villages that each have an individual resource that they harvest. And this is the individual system. It's a classical system studied in resource economics or theoretical ecology, for example, where the harvesting agent can exert an effort on the resource and gets a harvest rate in return, which depends on the state, on the stock of the resource. So if the resource is low, the harvest rate is also low, and vice versa. And then there's also different social processes in this network. There's social influence via imitation. So this is a social learning process where actors, villages can communicate, can meet each other, and then exchange information on what harvest success they had using their harvesting strategy. So either a sustainable low effort or unsustainable high effort strategy. And finally, there's social network adaptation. So it's a process where nodes can, villages can change from one strategy to the other. They change their network depending on the strategy of their neighbors. And to show this in a bit more structured way, we have this this social ecological model. There's the social network, there's the resources, there are the different interaction pathways, and the social dynamics takes place via homophilic network adaptation or strategy imitation, and the ecological dynamics is this classical renewable resource and linear harvesting dynamics. I should say because I didn't say it on the slide before, the network adaptation, that's a homophily process. So it describes the tendency of humans or organizations more generally to be connected to others which are similar in different aspects. So there's a tendency sometimes to break links, to break social ties to other actors which are dissimilar, and to connect instead to other actors which are similar. So it's really this idea that friends are often more similar to each other than people who are not friends. But this is of course just one process. It's not a universal. One could also add other processes like heterophily, for example. Now, what we find when we study this using again an ensemble Monte Carlo type approach, studying the dependence of the probability to converge to a sustainable state, where all nodes are in a sustainable state, depending on two parameters. We observe a clear phase transition between a sustainable island state and an environmental collapse state. And interestingly, the two key parameters that determine this are the social imitation timescale here and the technological divergence. They're faster social learning rates, faster imitation makes the system more likely to collapse. This is this great acceleration arrow. And also larger technological divergence, so a larger difference between the sustainable and the unsustainable harvesting techniques also makes the system more likely to collapse. We, I don't show this here, but we also studied how the system behaves close to this phase transition. And for example, there's a peak in convergence times of the model around this, which points at the phase transition being present here. And we can also approximate the properties, the location of this transition quite well using techniques of moment closure, for example, but there's also much more to be done here in terms of statistical physics analysis, certainly. One interesting aspect that I wanted to point out for this model is that when we also look at the network adaptation of the change in the change in social structure, we find that this is now the parameter on the x-axis. We find that there is it seems that in some cases this adaptation can stabilize the system in a sustainable state where otherwise it would collapse. And how does this look? So if we have a case of slow imitation, now there's social network adaptation is not so important. So the system is sustainable up to very high social network adaptation rates, where at some point a fragmentation transition happens at around 0.7 adaptation rate. But before, the system is always sustainable. But so there's this network disintegration regime, which is well known from adaptive auto models, for example. But when you go to regimes of faster imitation or faster social learning, there suddenly the probability to converge to a sustainable state is quite low if you have only a low network adaptation, and only an intermediate level of network adaptation succeeds in stabilizing the system in a more sustainable state. And this is quite an interesting property that also deserves more attention generally, I think. So this window becomes smaller the faster the imitation is, as you can see, when going from this red to the blue curve. So this is what we call here the safe operating space for fast imitation. Now we can finally add an additional layer to this and this is a governance layer. This is also quite interesting in an adaptive multi-layer network approach. And one motivation for doing this is the study of so-called adaptive polycentric governance networks. So this is the study of systems where there's not just one agent governing the resource users, but for example, assigning taxes to the users, giving laws to them and policing them. But there's multiple governance actors that interact with the users, but that also interact with themselves. What we did here is we took this model that I showed before, the so-called exploit model, and added this additional governance layer. And what these governance agents can do now, they can tax unsustainable behavior. So what they do is that each of them is connected to a number of users, of resource users, and each of them can assign taxes to unsustainable behavior. If it's a taxing, so to say, environmentally conscious governance agent, if it's an indifferent governance agent, there's no taxing. And the property of the governance agent to be taxing or indifferent can also change via social learning. So there's a symmetric social learning process in the governance level, as it is also there for the user level. And now we study the emergent dynamics of this more complex system. And this is now parameter plots for the for different combinations of relevant parameters. So it's again the user waiting time, which is the social learning related to the social learning rate, the rewiring rate, which is the network change, and the tax rate, which is now how high taxes to unsustainable behavior are. And what is interesting is that there's also in most cases, there's a quite sharp transition to be observed between these sustainable and unsustainable regimes, phases. And we also find that this, of course, depends on the size of the system, and these transitions become sharper when the system size increases, which is not shown here. And one interesting observation is that we can do analytical approximation here, again, using moment closure. For example, we can compute the critical tax rate, gamma crit here, where which is the tax rate above which sustainable states are always achieved. So there's this critical tax rate in this simulation of about 0.7, where below which two phases exist and above which only one phase of sustainable resource use exists. And however, one should point out that these moment closures work relatively well, but they suffer similar limitations as have been pointed out for the adaptive voter model, for example, by the group of Thilo Groß and others. And there are alternative techniques for approximations in these systems, which are probably more successful, but also more complex, more demanding. And there's more research to be done in this field as well. One finding that one can draw from this, before I close off, is that interestingly, if we compare a case of a so-called eco-dictatorship where a single governance node exists that always taxes unsustainable behavior, and we compare this to a polycentric governance network. So the analytical approximation was done here for the eco-dictatorship case here on the left-hand side, and we can compare these, and we find that there's a trade-off in a certain sense, that for the eco-dictatorship case, there is a certain critical tax rate above which sustainable behavior is always achieved, but this is in this case really high tax rates. This is 70% taxes, and also if you go to lower tax levels, the unsustainable regime, the size of the unsustainable phase is quite large. However, in the polycentric governance case, there is no critical tax rate, so there's always two phases exist for all tax rates, but the size of the undesirable, unsustainable state is smaller for most tax rates compared to the eco-dictatorship case. So there's a trade-off between safety and resilience, or in a certain sense here, which is quite interesting. I think also to study in other models and using more advanced methods of complex systems theory. Now, really finally to close off, I would like to point out a few open research questions and avenues that that have emerged from these studies. And for example, there's questions about the relation of this concept of social tipping in a broader sense, and how it relates to concepts and methods from statistical physics, so regarding phase transitions, critical behavior, particularly also in adaptive coevolutionary network models. There's the question of under which conditions can one expect early warning of approaching critical transitions in such systems, similar to what has been shown, at least in some cases, for more deterministic physical systems in critical slowing down. There's questions of structural stability of these models, and also to how can we move closer to get an intuition on what critical transitions or phase transitions to expect in certain classes of these adaptive coevolutionary network models, or broader classes of these network models. So including the structure of different phases that is to be expected, the universality classes, etc. There's the question about more extended notions of critical transitions in these systems, like rate-dependent tipping, so-called rate-induced tipping, which is increasingly studied in climate physics, for example, or the Pareto principle. So the question of what is a critical number of actors that is needed to initiate a desired transition. And finally, and then also linking to this notion of managing or achieving desirable states in these systems, there's the question of control, management, and governance of these systems. So how can desirable social ecological tipping dynamics, like a fast decarbonization of society, be fostered, or how can the undesired tipping dynamics, like a collapse of social order, be avoided? So what do our methods have to say on these questions? Yeah, finally, to sum up, these methods, I think, are very relevant tools for studying social ecological dynamics, ranging from the study of tipping cascades to social tipping points, and to also social ecological dynamics, like in these resource user models. The methods from statistical physics and more broadly network theory and complex system theory are very, I think, very, very useful for getting a deeper understanding of these systems, and particularly they are highly needed to go beyond black box agent-based models and other types of modeling approaches, like cellular automata, for example, that have been used in these contexts, but which are quite unsatisfactory in many ways, and have been criticized also on these grounds by many people. So it's desirable to reach a more detailed and a more satisfactory process of understanding comparable, say, to climate physics in the Earth system context, where we are also dealing with complex systems, but we can say much more than we could do with just a black box ABM. So we get a more deeper understanding of the underlying processes. Yeah, and of course, finally, the theoretical research on and these applications that I outlined can benefit from, hopefully, from cross-fertilization, for example, by generating new research questions for theory, but also for getting new, deeper insights into the application questions. And with that, I thank you very much, and yeah, sorry for being a bit over time.
Okay, thanks. Thank you, Jonathan, for this interesting and clear presentation regarding this important problem in our society. This is the problem of the climate change and the different approach to understand this how to solve this problem. So this is time to have some question. Raise your hands physically or electronically, or unmute the micro. Judith, please.
Thank you very much. Thank you very much for this talk. Excellent. It was very, very interesting. And we are looking forward very much to having your chapter in our volume 7 of our review volume series. My question is the following. That's about the first part of your talk. When you were speaking about network approach to identify roles of tipping elements in climate change. Somehow, I haven't got where from you take the structure of the network. Basically, how many nodes are in your network, and where from you take the structure, and what are the nodes?
Yeah. So we used here four different tipping elements where so the ocean circulation, the Greenland ice sheet, the Western Arctic ice sheet, and the Amazon rainforest, and we just chose this smaller system because we have quite a good, so for one, we know quite with relatively high certainty that these 4 elements actually are tipping elements, and they have this double-fold bifurcation structure in a macroscopic sense, or at least they can be described by this. And there's evidence also from paleoclimate, from past climate states, for example, that they have had these different states. So that was one reason for the selection. So we didn't include the candidates which are where there's much less understood and much higher uncertainty. So we took the most convincing candidates, and we ended up with 4. And the second is the interaction structure. So we used data from a paper by Elmar Kriegler and others who did an expert elicitation already in 2009. Actually, they asked many experts from climate science about the interactions between tipping elements and which processes are connecting them, and they also assigned kind of ratings on these processes where they thought this has a high uncertainty, this has lower uncertainty. Here we know this process is stronger than this one, and this information we used to generate the network structure. Yeah. And we also sampled from these uncertainties. So for example, we know that it's a well understood physical process that melting of the Greenland ice sheet leads to, of course, accelerated freshwater influx because the ice melts and then freshwater flows into the North Atlantic Ocean. And this makes the surface waters in the North Atlantic more fresh. So decreases salinity, and this weakens the circulation because the deep water formation relies on relatively dense water that sinks to the bottom of the North Atlantic. Yeah. And these types of physical processes we can list for each of the links in the network. And we also know, okay, here the strength is between 3 and 5, and for the other one it's between 7 and 10. Yeah. This is how we did, And
so basically, if I think about network, I can think that it is a complete graph of 4 nodes, and you have multiplex network with different layers of different processes.
Yeah, you could see it like that.
Yeah. Thank you.
Another question, comments, please. Okay, I have a question. When you define the social tipping element, you need to have or to identify a system in which they undergo a second order phase transition, no? In order to produce with a small chain on the microscopic parameter, you need to have a small chain in the global properties of the system, no? But you don't want to have a first order phase transition, no?
Yes, that's right. I mean, it's in most cases, most of the cases that we study, we get second order phase transitions. Yeah, I mean, but this is also something to. I think this is a level of discussion that many of these more applied people they're not even at that level, right? So this is, I think, for example, this links to one of these more broader questions that I pointed out, that I think it would be really great to get a more from the theory of statistical physics to get a better understanding of what phase transitions you can expect, first order, second order, or others for different classes of these models. When and if such a if such constraints can even be given in general.
Okay. Any more questions? So, well, thanks again, Jonathan.
Thank you.